In the previous video, we saw the uniqueness theorem. Okay, with this, the first half chapter theory equations are done. So now we'll solve some problems under this. Okay, so previously we have seen how to solve, how to check whether the given potential satisfies Laplace equation or not. Right? The type of problems you have seen under this is we have seen that some voltage potential equation will be given and you were just checking if del square V is equal to 0. If after doing del square V, if you get the answer as 0, you would say it satisfies. If it was not equal to 0, we would say it does not satisfy the Laplace equation, right? And for different coordinate systems, you have different Laplace equations. So those three equations are very important to remember here. Now the next type of problem that we're going to see is using the Laplace equation or Poisson's equation, that is minus rho v by epsilon. Okay, either by using these or these two, whichever is mentioned in the question, you are going to solve the problems based on that. Like you will be finding out the solution for potential, or you will be finding out electric field intensity, which is minus del V, right? Or you will find D, which is equal to epsilon into E, and you will also be asked to find charge density, which is equal to the magnitude of D in this case. Okay, in this problem, in this chapter, if they ask you to find surface charge density, you should know that it is equal to the magnitude of D. Okay, so these are the things that will be asked in this type of problems. Other than this, you also have later on you will see some problems where you will be supposed to calculate the capacitance value. Okay, for that what you should do is you will be finding V value. Okay, and you will be also finding the charge value, and if you know charge and potential, the capacitor can be calculated, capacitance value can be calculated. Okay, uh, because we know charge is nothing but C into V, so your C will be charge by potential. So by using this equation, your capacitance value can be calculated, but we'll see about this later on, the capacitor value. For now, we're going to solve some simple problems based on these equations, these relations. Okay, so first one is the given the region between two concentric right circular cylinders contains a uniform charge density rho, and they have asked you to solve the Poisson's equation for the potential in the region. Okay, so here they're asking you to find potential value. Okay, you need to get the equation for potential, and to get the equation for potential, they are telling you that you are supposed to use Poisson's equation. And Poisson's equation is this. So you have the equation del square V is equal to minus rho V by epsilon. Okay. This is the Poisson's equation. You have to do some simplification to this equation and get the solution for potential. Right. And now just check whenever you're using Laplace or Poisson's, you need to know which coordinate system they're talking about. And clearly it is given right circular cylinder, which means they're using cylindrical coordinate system. And if you have a cylinder, then the potential is going to be perpendicular to this. So it is going to be in the R direction or AR direction, radial component. Okay. And in cylindrical coordinate system, sorry, you need to know what is the del square V equation in AR direction. Okay. Your general del square V equation will be 1 by R, dou by dou R of R, dou V by dou R, plus 1 by R, dou V by dou phi, plus dou V by dou Z. Right? Out of this, they have clearly told you that you are going only for the R direction component. So you will be having only this much. Okay. So you will be having only the R component here. These two will not come into picture. Right. So now your del square V is equal to 1 by R, dou by dou R dou V by dou R. And that is equal to minus rho V by epsilon. Okay. And here they're given that the density is equal to rho. Instead of rho V, the symbol rho is used here. Whatever is mentioned in the question, that you're supposed to substitute it. Okay. So rho V is nothing but rho according to the given question. So now let's rewrite it. I have 1 by R dou by dou R of R into dou V by dou R. On the other side, I have minus rho by epsilon. I'll take this 1 by R to the right hand side. So it becomes dou by dou R dou V by dou R. That's equal to minus rho into R by epsilon. This R is taken to the other side. Right? Next, what is supposed to see? What I'm trying to find is this v value. I need to get v. So for that, I have to eliminate uh, each of these terms one by one, right? So first, I'm going to eliminate this first differentiation, that is dou by dou r. So to eliminate this differentiation term, I have to integrate on both sides. Okay. To eliminate the differentiation, you have to integrate on both sides. So after the integration, this dou r gets cancelled. So I'll be having r dou v by dou r. Only this term remains, right? And integration of this. Integration of minus rho into r by epsilon with respect to dr. So integration of this rho by epsilon is constant here. Integration of r is r square by 2. And remember, whenever you're integrating in this particular chapter, if you're doing integration of Poisson's or Laplace equation, you need to include the integration constant. Okay, this is compulsory here. Whenever you're solving problems in Laplace or Poisson's equation in this chapter, you have to include the integration constant. That is C1 here. Every time you do integration, a constant should be added along with that. Okay. So now I have r dou v by dou r equal to minus rho r square by 2 epsilon plus C1. Okay. I'll take this r to right hand side. So I will get dou v by dou r that is equal to this r gets divided to the both terms here. So minus rho by epsilon r square by r, so it becomes r by 2 plus c1 by r. I just took this r to the other side. Okay. So now I have one more differentiation. So if I remove that one more differentiation, finally I will be able to get the potential here. Okay. So for that, again, I have to do integration on both the sides. So I'll get v is equal to now integration on this side with respect to dr. Okay, so the first term integration is going to be minus rho by 2 epsilon is constant. Integration of r square is r square by 2 plus c1 is constant. Integration of 1 by r is natural logarithm of r. Okay, and since you have done another integration, I need to add one more constant here. Okay, so finally I'm getting the potential equation as minus rho into r square by 2 to the 4 epsilon plus c1 into natural log of r plus c2. This is the equation I got for potential. Okay, so I hope it is clear. So whenever they're asking you to find any of the parameters, that is potential, intensity, density, or surface charge, or capacitor, anything it is, you always start off with the either Laplace equation or Poisson's equation. If you are going to use Poisson equation, then rho v will be given in the question. If nothing is mentioned about volume charge density, then directly start using the Laplace equation. If rho v is not mentioned in the question, then you go for Laplace equation. That is this. If rho v is mentioned in the question, then you have to use Poisson's equation. You start with this either Laplace or Poisson and check which coordinate system it is. According to the coordinate system, you have to write the del square v equation. And also have to check which direction they are asking you to find out. If it is if it is Cartesian system, is it X, Y, or Z? If it is cylindrical system, is it R, Phi, or Z? And if it is spherical system, is it R, theta, and Phi? So based on that, only one of the term will be there in your del square V equation. And then one step at a time, you have to eliminate the rest of the terms in order to get the potential equation. If you have a differentiation, you need to integrate so that you can cancel out the differentiation term. And very important thing to remember here is every time you do an integration, you need to add a integration constant to it. Okay, so I hope this problem is clear now. Okay, we have similar problems starting from this part. And in coming problems, what we do is you have this equation, right? The C1, C2 are constants here, which can be calculated with the help of some initial conditions. Okay, so you will see that in the next problem. Some initial conditions are given, some conditions are given. Using that, you will be able to calculate the unknown C1 and C2 values. And once you know the C1, C2 values, you have to put it back in the V equation. Okay, so we'll do that problem now. First, we'll do some simple problem, then I'll come back to this question. Okay. So here is a question now. They're given two parallel conducting discs are separated by a distance of 5 millimeter at z equal to 0 and z equal to 5 millimeter. If V is 0 at Z equal to 0 and V is 100 volt at Z equal to 5 millimeter, find the charge densities on the disk. Sorry. So here the question is to find out the charge density. Charge density is nothing but rho s. Okay. So if you want to find rho s, you need to calculate first D, because rho s is nothing but magnitude of flux density. And if you want D, you need to first calculate E, which is epsilon into E. Okay. And in order to know E, you need potential. And for potential, you can either use del square V equal to 0 or del square V is equal to minus rho V by epsilon based on what data is given in the question. And you can see that there is nothing mentioned about your volume charge density in the question. Right? They have not given rho v anywhere in the question. So I will not use this equation. I will have to go for Laplace equation now. Okay. So you are starting off with Laplace equation. Del square v equal to 0. Right. The next thing you need to know here, they have given there are two conducting disc which are separated by a distance, and they have mentioned only z value, which means they have given only z-axis value here. Okay, so if it is a only z-axis value, I can assume that the system is Cartesian system. Okay, I can assume that it is in Cartesian system, and in Cartesian system, what is your del square V equation? You have to go back to the starting. Three systems, you have different Laplace equation, right? Out of that, you are selecting Cartesian now. So your Cartesian system will be del square V by del x square. There's a dou square V by dou x square plus dou square V by dou y square plus dou square V by dou z square. And here it is mentioned only in the z axis. So these two terms will not be there for the Laplace. Okay, since you have only z value here. So now I can write del square V is equal to dou square V by dou z square, and this is equal to 0. I hope you're getting it. First step, check whether you're supposed to use Laplace equation or Poisson's equation. If nothing is mentioned about the rho v value, then directly go for Laplace. Second, you have to check which coordinate system it is, Cartesian, cylindrical or spherical. And based on that, you have to write the del square v equation. And out of the three terms, you have to choose one of them based on the data mentioned in the question. In this case, they've given only z-axis, so I have chosen only the z-axis value for del square v. Okay, and that is equated to 0. Next step is I have to simplify this so that I can get the equation for potential. So as I told you before, if I want V, I have to eliminate one by one all the terms that are there. So here if you see directly, first term is going to be the differentiation dou by dou z. So I have to integrate it once. Here you have two differentiations. Okay, so first I'm going to integrate it once. When I integrate it once, one of the differentiation gets cancelled. I will get only the other differentiation, so dou v by dou z. And on the right hand side, integration of 0 is 0. It just gets added with one constant value C1, integration constant. This integration is 0. Along with that, there is going to be plus a integration constant C1. Okay. Again, I have to do integration to remove the last differentiation. So if I do integrate on both the sides, I'll get finally V here. And this will be integration of C1 with respect to dz plus the integration constant. So I'm getting V is equal to C1 into Z plus C2. Let's say this is our equation 1. This is not the end of the solution now, because in the question they've asked you to find rho S. Okay, if you want rho S, you have to calculate the other parameters also. But you see in this question, there is one more thing that is mentioned. They've given here this part of the question. Some value, initial values are given. They're saying that the potential is 0 when Z is equal to 0. Second is the potential is 100 volt at Z equal to 5 millimeter. Right? So I have to use these two conditions to find this C1 and C2 values. Okay, that is what I was talking about. Some initial condition will be given which can be used to calculate the constants. And then once you get the constant value, you should put it back in the main equation. Okay, so I will use the first case, that is V is equal to 0 at Z equal to 0. So I will put this values in this equation 1. So I'll get 0 is equal to C1 into 0 plus C2. From this I get to know that C2 value is 0. Okay. Second condition is given as V is 100 at Z is equal to 5 millimeters. Okay. So V is equal to 100 and this is C1 into 5 millimeters plus C2 I just calculated now, it is 0. Okay. Simplify this. If you simplify this, you will get to know that your C1 value is equal to 100 by 5 into 10 power 3. So you will be getting the answer as 20 into 10 power 3. Sorry, this is actually 100 divided by 5 into 10 power minus 3. So it becomes 20 into 10 power minus 3. This is what you're going to get for C1. So I found out C1 and C2. I'll put it back in the first equation. So V is equal to 20 into 10 power 3 Z and C2 is anyways 0. Okay. So this is the equation I got for potential. Right? After finding out C1, C2 using the given conditions, I have put those values back in the main equation and I got the solution for potential in moles. Okay. Now once I know the potential, the next thing I'm supposed to calculate is intensity, which is minus del into V. Okay. And again, you have to now write the equation for del V. Okay, del V equation, which you have seen in module 2, the gradient. Okay, gradient of potential. You have an equation there. So minus del V in Cartesian system will be minus of dou V by dou X AX plus dou V by dou Z, dou V by dou Y AY plus dou V by dou Z AZ. And as I've already told you, here we have only Z axis values. So X and Y components will not come into picture. You will be having only minus dou V by dou Z AZ. Okay, so whatever V you have calculated just now, substitute it here in this equation. So I'll get E is equal to minus dou by dou Z of V is 20 into 10 power 3 Z AZ. So differentiation of this with respect to Z will give you minus 20 into 10 power 3 AZ volt per meter. Okay, this is the answer for your intensity. So once you get intensity, the next thing is you're supposed to calculate uh, flux density. Okay, and flux density is nothing but epsilon into E. Here nothing is mentioned about epsilon R. So I can assume it is free space. So epsilon naught into E. Epsilon naught is 8.854 into 10 power minus 12 into the E value whatever you got, minus 20 into 10 power 3 in AZ direction. So the solution for this is equal to minus 1.7708 into 10 power minus 7 in AZ direction, and the unit is coulomb per meter square. Please substitute it, calculate it using a calculator, multiply these two. Your answer should be minus 1.7708 into 10 power minus 7 in AZ direction. And I told you the charge density is nothing but magnitude of this, magnitude of your flux density. And out of this portion is a magnitude and this is direction. So finally your answer should be minus 1. Sorry, I'm talking about magnitude, right? So irrespective of the sign, I need only the value here. So it is 1.7708 into 10 power minus 7 coulomb per meter square. Okay, you have to ignore the sign because I'm taking magnitude only, modulus of that. Okay, so your answer is 1.7708 into 10 power minus 7 coulomb per meter square. This is how we calculate the surface density. You need to know the relations. For rho s, it is magnitude of D, D is epsilon E, E is minus del V, and for V, you're supposed to use either Laplace or Poisson's equation. Okay, so this is one example where boundary conditions or the initial conditions will be given, which is used to calculate C1, C2 constants of integration and substitute it back. Right? So we'll move on to the next problem here. In this, they've asked you to find only the potential value at a certain point for the field of two coaxial conducting cones with conditions are given. Initial conditions are given here. Okay. and they've given it as coaxial conducting cones. But if you see the conditions, they're talking with respect to theta. Okay. Now, first of all, identify whether to use Laplace equation or Poisson's equation. Nothing is mentioned about rho v, volume charge density, right? So I'll have to go for Laplace equation only. Del square v is equal to 0. Okay. Since nothing is given about rho v, I cannot use Poisson's equation. I have to go for Laplace equation. Second thing is identify the coordinate system. So here if you look at the condition, it is mentioned theta. And theta comes only in spherical. Right? Theta comes in spherical coordinate system. And since it is only theta, the spherical coordinate, the direction is supposed to be a theta. Okay, so you have to write the del square V equation in spherical system. And out of the three components, that is AR, A theta, A phi, you have to choose only the theta component in the equation. Okay, and the theta component in the equation is 1 by r square sine theta, dou by dou theta of sine theta, dou v by dou theta. Okay, so this is the theta component in spherical coordinate system for del square V. This is equated to 0. Now, next step is common. You just have to do step-by-step simplification to get potential equation. Okay. So first I'll take this term to the other side. So 0 into r square sine theta becomes a 0. So I'll have dou by dou theta of sine theta dou v by dou theta equal to 0. Now to remove this, I have to integrate on both the sides. So I'll get sine theta dou v by dou theta here. This gets cancelled. Integration of 0 is 0. I'll just get the constant of integration in this case. Okay. And next, this sine theta will be taken to the other side. So dou v by dou theta is equal to C1 by sine theta, which implies dou v by dou theta is equal to C1 into 1 by sine theta is cosecant theta. Okay. Now to remove this differentiation, again I have to integrate it. So I will get V is equal to integration of C1 cosecant theta with respect to theta plus second integration constant. So I will get V is equal to C1 into, you can check the standard integration results, okay. Integration of cosecant theta is natural log of tan theta by 2 plus the second integration constant. Okay, you can check the standard integration results. You need to know all these integration results. Okay, integration of cosecant theta is natural log of tan theta by 2. So let's call this as our first equation. Potential equation is done now. But that is not the end, because they're not asking you to find the equation, but they're asking you to find the value of potential at particular point. So you have to substitute the points. So before that, I need to know what is this constant value, C1 and C2. So for that, we'll use the initial conditions which is given here. Okay. The first condition is V is equal to 50 volt when theta is equal to 30 degree. Okay, they're given V is 50 volt when theta is 30 degree. So I'll substitute these values in equation 1. I'll get 50 is equal to C1 into natural log of tan of 30 by 2 plus C2. Okay, so you substitute this in the calculator, simplify it. I will be getting the answer as 50 is equal to the value. Natural log of tan 30 by 2 will give me an answer of minus 1.3169 C1 plus C2. So I'll call this equation as A. I cannot directly simplify it, okay? So I got one of the equations. Second condition is given as V is equal to 20 volt when theta is 50 degree. So 20 is equal to C1 into natural log of tan 50 by 2 plus C2. So this is going to give me 20 equal to minus 0.7629 C1. Calculate this value. It will be minus 0.7629 plus C2. I'll call this as equation B. Simultaneously solving these two equations will give you the constant values. Put it in calculator, solve these two equations. I will get C1 as minus 54.1516 and C2 will be minus 21.3122. These are the constants value you're going to get. So once you get the constant, your equation for potential will now be, instead of C1 it is minus 54.1516 in this. In first equation, you have to substitute these two values. Ln of tan theta by 2 plus, C2 is minus, no? So minus 21.3122. So this is the equation you got for potential. Again, this is not the end because they're asking you to find the potential at this point, 2, 1, 3. I need to use these points. At this particular point, I need to know what is the value of the potential. Okay, so I got the final equation, but now if you just check the values that are given, it does not have any theta or phi value. It is not in degrees, right? Which means actually these values are given in XYZ coordinate system. This is X value, Y value, and Z value. But what I want here is theta, which is in spherical system. So you need to know how to calculate this theta using like you need to convert these points from Cartesian to spherical system. Okay, so you need to convert these points from Cartesian to spherical system. And if you remember, the equation for theta is equal to cos inverse of z by r, where r is equal to root of x square plus y square plus z square. I have given this equation, or even sir has mentioned this equation in the vector algebra first part, Cartesian systems. Okay, so you need to know these equations. Using these two equations, you can find out what is theta value. First, you calculate r value. Okay, r is root of x square plus y square plus z square. That is root of 2 square plus 1 square plus 3 square. So you will be getting the answer as 3.7416. Then here you should put that value here. Cos inverse of z is 3 and r is 3.7416. So you're getting the theta value as 36.698 degrees. Okay. Now we can calculate V minus 54.1516 into natural log of tan of 36.698 degree by 2 minus 21.3122. Theta value, whatever you calculate, substitute here. So finally your answer for potential will be 38.4507 volts. Okay. Simplify this using a calculator, find out the result. Whenever you have degrees, you have to keep your calculator in degree mode. If you have pi, in terms of pi, then you keep your calculator in radians mode. Okay. So this is how you solve this question. So main thing you need to know here is the integration result. Integration of cosecant theta is tan theta, natural log of tan theta by 2. Okay, the start procedure is same. Use the given conditions to find out C1, C2 value. Once you get that, put back in the main equation. And if some point is given, you have to use those coordinate values, axis values in the equation and simplify it to get one single value like this. Okay, so this is how we solve this problem. Right? So we'll go back to the second question which I have mentioned before. So here in this question they've given in free space rho v is equal to 200 epsilon naught divided by r to the power 2.4. Okay, so the first part of the question, there are two subparts here. First one is you're supposed to use Poisson's equation to find the potential as a function of r. They've mentioned find v as a function of r, which means whichever coordinate system you're going to consider here, it should be in r direction, ar direction only. Okay, so here you can assume it is in it has only r component here, so we can consider spherical coordinate system. Okay, so we can assume spherical coordinate system, and as you can see rho v is mentioned here, so you have to consider Poisson's equation. Del square v is equal to minus rho v by epsilon, and free space is it is free space, so it is epsilon naught. Okay, and whatever rho v value is given, you can put it here, minus of 200 epsilon naught by r power 2.4 divided by epsilon naught. So these two gets cancelled. So you have minus 200 by r power 2.4. And del square v, let's consider spherical system here in AR direction. So del square v will be 1 by r square dou by dou r of r square dou v by dou r. That is equal to minus 200 by r to the power of 2.4. Okay. So further simplification is the same as before. One by one you have to eliminate the you have to do the steps to eliminate the terms, get the equation for potential. Okay, first we'll take this r square to the other side, so it becomes dou by dou r square dou v by dou r, that's equal to minus 200 by r to the power 2.4 into denominator will go to numerator on the other side, which gets simplified to you have r square by r to the power 2.4, right? If you simplify it, you will be getting minus 200 by r to the power of 0.4. That square will get cancelled, only 0.4 will remain, right? Now to remove this, I have to integrate on both the sides. So I'll get r square dou v by dou r on this side. And here integration of this term. Minus 200 is written outside. Integration of r power 0.4 with respect to dr. Plus integration constant, C1. Okay. So r square dou v by dou r is equal to minus 200 into integration of r to the power 0.4 will be, you can just take it like this, r power minus 0.4. In the denominator you have r power 0.4, so if you take it to the numerator it becomes r power minus 0.4, and integration of this will be r power minus 0.4 plus 1 divided by minus 0.4 plus 1. Okay, normal integration, if you have r square, how do you do? R power 2 plus 1 by 2 plus 1, right? That is how you get r cube by 3. Same thing is done for this. Just add plus 1 to the power, as well as take that power in the denominator. Okay, so you will be getting the answer as 0.6 by, I'm sorry, r power 0.6 by 0.6 plus your integration constant. Okay, so our further simplification can be done. I'll keep the dou v by dou r on this side. I'll take r square to the other side. And if I do this 200 by 0.6, I'll be getting minus 333.33. Okay, I'll keep this r square here only for now. Here it is r power 0.6 plus C1. I've just done 200 by 0.6. Okay, that gives me minus 333.33. Right? So further, what I'm going to do is, before I do the integration of this, I will just check what is the condition given in the question. As you can see, the first condition given here is not with respect to potential. They're given E here, right? So I'll have to use this right now. R square ER is 0 when R is 0. So I have to do something to get that E in this equation. As you can see here, there is no E term. There is only potential V, right? I need to do some substitution to get E in this equation so that I can use that condition here. Okay, and that substitution is, we all know that E is equal to minus del V, right? And in spherical system, in AR direction, the del operator will be minus del V will be dou V by dou R into AR. Now can I say this is your magnitude and AR is the direction, right? So in place of ER, what do we have? Dou V by dou R. Okay, so I will now substitute that. I have minus dou V by dou R. So instead of dou V by dou R, can I put minus ER here? In which case it becomes minus R square ER. So I have replaced potential with respect to intensity. Now I'll be able to use the first condition. Okay, other side there is no change. So you still have this values. Okay, why did I do this? Because the conditions what are given here, no, one of them is in potential, but the other one is in terms of intensity. So I cannot just keep it in potential and solve it. I'll have to replace it in terms of E so that I can use this condition there. Okay, and for replacing it only, I have done this substitution here, right? So what is the condition given? They have given R square ER is equal to 0 for R is equal to 0. So I'm going to use this condition now in this equation. So I will get 0 is equal to minus 333.33 into 0 to the power 0.6 plus C1. This implies that your constant is 0. C1 is 0. Okay, I'm going to put this back in this equation now. I have minus R square ER that is equal to minus 333.33. Okay, sorry, 1 second. If you compare the two equations, we find that ER is equal to dou V by dou R. So here there is no need for negative sign. Okay. Instead of dou v by dou r, you just have to put er here. There is no negative sign here, okay, on this side. And now if I put the C1 value, C1 is anyway 0, so I don't have to include anything. Okay, this is what I have. Now to move forward, again I have to go back to the previous equation. That is, instead of ER, I have to get back to potential, because further simplification can be done only for potential, right? So I will again write it as dou V by dou R. And this side I have 333.33 R power 0.6. Okay, so now I'll take this R square to the other side, which will give me dou V by dou R is equal to minus 333.33 R power 0.6 divided by R square. So if you simplify that, you will get R power 0.6 by R square will be R to the power 1 by 4. Okay, that is 2 minus 0.6. 2 minus 0.6 is 1 by 4. Now, further I have to do again integration so that I can get back the potential here. So I will get V is equal to, after next integration, I will get V is equal to minus 333.33 integration of R power 1 by R power 1.4 with respect to dr plus second integration constant C2. Okay, so if you do the integration of this, you will get minus 333.33. This will be R power minus 1.4 plus 1, so it is 1 by minus 0.4 into R power 0.4 plus C2. You just simplify it, you will get to know. Okay, if you do this same procedure as what you've done for the first integration, you will be getting this answer here. Okay, minus and minus becomes plus, and 333.33 divided by 0.4 is going to be 833.325 divided by R power 0.4 plus C2. Now we'll use the second condition that is given in the question, that is V is equal to 0 when R becomes infinity. So if I use that here, V is 0, that is equal to 833.325 divided by R is infinity to the power 4 C2, power 0.4 plus C2. Anything divided by infinity is going to be 0, which implies your C2 is also equal to 0 now. So finally, you are getting the potential equation as 833.325 by R power 0.4 in volts. Okay, so this is the answer you get for potential. Okay, so hope you've understood how to solve this problem. Just remember, check the condition, in what terms the condition is given. Based on that, you have to use that term in the equation. If it is not there, you have to replace it by using other relations. Okay, and once that is done, the rest of the process all same. Right? So this was the first part of the question. In the second part of the question, they have asked you to repeat the process. That is, again, they're asking you to find the potential only, but this time you're supposed to use Gauss law and line integral. Okay, so you have to use a different method to find out potential. But in the end, you will see that irrespective of what method you're using, the equation for potential is going to be the same. Okay, so now we'll do the second part. That is, we are going to start with Gauss law and we are going to use line integral for that, and we'll find out the potential equation. Okay, so according to Gauss law, we know del dot D is equal to rho V. This is the second part of the question where we are going to use Gauss law. Okay, del dot D is equal to rho V, and del dot D can be written as epsilon naught into E bar, that is equal to rho V. Or epsilon is a constant which can be kept outside. So you'll get del dot E is equal to rho V, or del dot E becomes rho V by epsilon naught. And in the question, rho V was given as 200 epsilon naught by R power 2.4. Whole thing divided by epsilon naught. So this two gets cancelled. We will get 200 by R power 2.4. Right? So now you have del dot E is equal to 200 by R power 2.4. Right? So next I have to go for del dot D, divergence equation in a spherical system for only AR component. Okay, I don't want the other two. I want only the R component. So R component for spherical system, divergence is 1 by R square dou by dou r of r square er. That is equal to 200 by r power zero point 0.4. This r square can be taken to the other side, which will give you dou by dou r of r square er is equal to 200. If I just simplify it, I'm going to get the answer as r power 0.4. Okay. And now to remove this integration, remove this differentiation, I have to integrate on both the sides. So I'll get r square e power r, and here it becomes integration of this term. The result I'm going to write directly. So it is going to be 200 into r power 0.6 by 0.6 plus integration constant. Okay. Now I can directly use the given condition, that is r square er is 0 for r is equal to 0. This was the first condition, no? If I use this, I'll get, if I substitute that, I'm going to get C1 equal to 0. Okay. Next step, r square er is equal to 200 r power 0.6 divided by 0.6. C1 is 0, so I'm not going to write anything here. Now I can take this r square to the other side. After simplification, I'm going to get 333.33 by r power 1.4 after simplification. Okay, this is the magnitude of your intensity, but my total intensity is going to be magnitude as well as direction. So I can write this as 333.33 by r power 1.4 in AR direction. Okay, but what we're trying to find out is potential. And if I know E, the equation to find potential is line integral of E dot dl. Okay, this is the equation we have which relates potential and intensity. If potential is given, intensity is calculated using this equation. But if intensity is given, the potential is calculated using this equation. Okay, so I have E, I need to know the length, and since we are talking about R direction, the length is going to be dr AR in spherical system. After taking dot product, AR dot AR becomes 1. So I will be getting line integral of 333.33 by r power 1.4 dr. So integrate this with respect to r. So your final solution is going to be 333.33 divided by minus 0.4 r power 0.4 plus second integration constant. Every time you do integration, default add an integration constant in this chapter. Okay. If you simplify this, 1 by r power 1.4 is nothing but r power 0.4 by minus 0.4. Okay. So now you have the equation for V as okay, I missed one more negative sign. The equation here you have E is equal to minus del V, no? So V will be minus integral of E dot dl. So you have a negative sign here in the main equation. So minus minus becomes plus. You have 333.33 by 0.4 into r power 0.4 plus C2. So now we can use the second condition, V is equal to 0 when r is equal to infinity. With that, you will get C2 also as 0. If I substitute that, anything divided by infinity is 0. So C2 becomes 0. So your final equation for potential is 333.33 divided by 0.4 is 833.325 divided r power 0.4 in use. Okay. So if you remember, this was the same result what we got from the previous method also, that is using Laplace or Poisson's equation, right? So irrespective of the method that you choose, the potential value is going to be the same, but the methods are different. In first case, you used Poisson's equation, you simplified it, you calculated the C1, C2 using the given conditions, and you found out. In this case, you have used Gauss law and line integral, and also you have used the initial conditions to get the final solution. Okay, so this is how you solve such problems. I'll be stopping this video for here. In the next video, we'll be continuing with some more problems. Thank you.